Well, hi. This is going to be an example just like coiling up a rope or pulling up a chain or something like that, where, gosh, the amount of work decreases a little bit because every time you pull up another link of the chain or another foot of the rope, there's less weight to carry. There's less distance that some of the rope has to travel and more distance that others have to travel. So we look at the work increments, each little bit of it. We realize that's going to be the force increment times the distance that's there. Now, that means we have to figure out what is that force, and it's pretty much the weight of something. But that little increment that we're going to be looking at is just some short little distance. Now, our rope in this example is 1/10 of a pound per foot. So if you just take that times the number of feet, or kind of the change in distance there, that'll tell you exactly how much that increment's going to weigh. The other important thing here is the distance that it's going to travel. So if we think of the bottom of the rope as a height of 0 and the top of the rope as a height of 165 feet, that means the distance that each part travels will be 165 minus y. What? Well, yeah. That means if you're looking at a tiny little section of rope that's about 1 foot from the bottom, it actually has to travel 164 feet up to the top where it's being pulled up and coiled. If you're looking at a point that's somewhere in the middle, it only has to travel 82 and a half feet. The distance that it is moving up is equal to the total length minus y. And this gives us a chance for part A to set up a very nice integral that can deal with this. If we want to find the actual work done, we're going to integrate all these work increments here. We're going to take that distance, 165 minus y, times the force increment, which is pretty much 1/10 of dy. And there we have an equation. The only thing left to do at this point is maybe to put in some limits here and say we're going to integrate it from 0 to 165. I'll leave the actual integral up to you. I don't consider that too important at the moment. That brings us to part B. Does it make a difference if we only coil up half the rope? Well, sure, it does. And most of you would guess correctly that, the force really hasn't changed that much. The distance it traveled hasn't changed that much, right? Except for these interesting little facts. That's supposed to say 82.5 up top. It doesn't really look like it. But you have to realize we've now coiled up half the rope. What happened to the other half? What happened to the bottom half that's still dangling down? Didn't we have to pull the weight of that up? Well, that's really nice. That is a constant weight, a constant force, half of the rope, literally half of the rope, which weighs 1/10 of a pound for each of the 82 and a half feet of the bottom half of the rope. And I believe the distance that it traveled, well, if I coiled up half the rope, that means the bottom half was pulled up 82 and a half feet and it's still dangling there. So we have the work of the bottom half of the rope in blue, and we have the work used to pull up the top half of the rope in black. Finally, part C, I can't see how much time I have left on this funny little video, but we have the exact same situation as part A. So we are going to write down the exact same thing. Hey, look, we're just coiling the rope, right? No change, no difference there, except we happen to have this weight on there. Someone threw my rack onto this mess, and oh well, it's an extra 10 pounds that traveled 165 feet. This is not a variable amount of work. That is one set force, one weight that doesn't change, and one distance that's the same for every part of that weight. So in each of these problems, we have the variable part of the work with the integral. And in parts B and C, we had some portion of this that was a set amount of work. And that's how we solved those three problems.